All right, so here we are in 14.4, where we're talking about tangent planes and linear approximations. So in single variable calculus, you talk about the derivative in the context of a tangent line. And tangent line is used for something that we call a linearization in that class. And that's something that we're going to try and generalize here, but we need to start by thinking of what the analog to a tangent line would be to a surface. Tangent lines are lines that are tangent to a curve, and curves are the graph of a function of a single variable, typically. A curve, like a plane curve. Functions of two variables are generally going to give us surfaces. So instead of talking about tangent lines, what we have instead are these things called tangent planes. Back in the previous section, 14.3, where we gave kind of that geometric interpretation of what the partial derivative actually represents at a particular point P. It represents tangent lines to the surface given by our two variable function at that point P, and those tangent lines can go in different directions. There's the one can go in the x direction, one can go in the y direction. And in that image that we showed in that previous section, those tangent lines were labeled T1 and T2. If you take a surface like this one, this blue surface, select a point and find those two tangent lines, the two that we referred to using those partial derivatives with respect to x and y, T1 and T2, then the plane that contains both of those lines, and it'll be just one distinct, unique plane that contains both of those, is called the tangent plane to the surface S, in this case, at that point P. And it looks the way you would expect it to. It just kind of touches the surface at that point, similar to how a tangent line will just sort of touch a curve at a given point. Now, our goal here is to come up with the equation of a tangent plane to a particular point on a surface S if we're given a function f of xy that gives us the surface S. So let's suppose that we have that, some function f of xy, z equals f of xy, and let's suppose that surface that we get from that function contains the point x naught, y naught, z naught. That means f of x naught, y naught is equal to z naught. Okay, so because this point is on the surface and we want to find the tangent plane to this specific point, then the equation of that plane would have this form. We showed all the way back in chapter 12 what the equation of a plane looks like, containing a particular point, and this is what it would look like. A, B, and C are some unknown constants. Now, we want to put this in a slightly different form. So what I want to do here is solve for z minus z naught. I want to isolate that. And I can start by dividing everything by this c here, and then subtracting these terms over to the right. That means I'm going to change what these constants look like. So to keep things simple, because this constant, once I divide by c and subtract it over, is going to look like negative a over c. That's going to be like the new coefficient here. Negative b over c will become the new coefficient here after doing all that solving. So I'm going to define new constants, lowercase a and lowercase b, to be exactly those two numbers so that we get z minus z naught equals this. A times x minus x naught plus b times y minus y naught. Okay? Now, let's consider that tangent line T1. Okay? The tangent line T1 is the intersection. This is based off of what we saw back in the previous section. It's the intersection, the curve of intersection between our surface S and the plane y equals y naught. Y naught because that's the y coordinate of the point that we're slicing through. Okay? But if I wanted to come up with the equation of that curve of intersection, I could do it by simply making this substitution in the equation for my plane. Okay, so this vertical plane intersects this tangent plane, and I get the equation by substituting y naught in for y. That causes this term to go to 0, giving me this. Z minus z naught equals a times x minus x naught. Now remember, what we're looking at is the intersection of two planes. So that intersection is not just any curve, it's a line. Namely, it's this tangent line, T1. And so this we recognize as the equation of a line. It's the equation of a line in point-slope form, which we talk about in Algebra 1. But if this is the equation of a line in point-slope form, then this lowercase a would be the slope of that line. That's what this point-slope form tells us. However, we already know how to come up with the slope of t1 using partial derivatives. According to the work that we did previously, and I can see I used a's and b's where I needed x naughts and y naughts. So let me change that. That should be x naught, y naught, x naught, y naught, x naught, y naught. I use a's and b's later in this section, so that's where that got mixed up. The slope of t1 is fx of x naught, y naught. And so that slope is a. A is equal to fx at that point, x naught, y naught. You can go through a similar derivation and show that the other unknown constant up here, this b, is, again, that would be the slope of t2, which we already know is fy of x naught, y naught. The partial derivative gives us that slope. So making some substitutions, substituting those partial derivatives in for these now known constants, a and b, this is the equation of your tangent plane at the point x naught, y naught. And there's a little bit of explanation up here. Suppose f has continuous partial derivatives. That allows us to use these in this equation here. But z minus z naught equals fx times x minus x naught, fx of x naught, y naught times x minus x naught plus fy of x naught, y naught times y minus y naught. Okay, now this is a totally valid way to write the equation of your tangent plane, but for some purposes that we're going to look at in a little bit later in this section, sometimes it's useful to isolate the z and to also notice that z naught is the same thing as f of x naught, y naught. Remember where z naught came from. We're talking about a point x naught, y naught, z naught on our surface, but the surface is determined by that function f. So f of x naught, y naught would have to equal z naught if that point is going to be on that surface. So substituting this f of x naught, y naught in for the z naught here and then adding that over gives me this alternative form for the equation of our tangent plane. This would be a constant. Okay. So let's do an example. I want to find the equation of the tangent plane to this surface at the point -4 to -1. Surface is given by the function z equals x over y squared. So what do we need? This is our function, and we need our partial derivatives with respect to x as well as with respect to y. So I'm going to call that zx. What is zx? Partial derivative with respect to x means I hold y constant, and that would be 1 over y squared. What about zy? What would that be? Well, now I'm holding x constant, and I differentiate with respect to y, giving me -2x over y cubed. Okay? Now, we're supposed to evaluate not just zx and zy, but according to the equation of our tangent plane here, which is using fx and fy, we have to plug in the x and y coordinates of the point that we want this tangent plane to appear at. So specifically, I want zx of -4, 2. -4, 2. And what would that equal? Well, zx, the function zx, only uses a y, so I'm just plugging the 2 in, and that would give me 1/4. What about zy of -4, 2? Okay, well that would equal -2 times -4, so that's 8 over 2 cubed, that's 8, that would equal 1. Okay, so one other thing that we need is z naught, but we have that already, that's -1. So putting all of this together, what would the equation of our tangent plane be? And again, remember, we can use either this form or this form. It doesn't really matter. So I'm going to use this form, the one that's given in your book, z minus z naught. That would be z minus -1, so really it's z plus 1, equals zx of -4, 2, which is 1/4, times x minus my x coordinate here, which is -4, so I'm going to say +4 there, and plus zy at -4, 2, which is 1, times y minus my y coordinate 2. Okay. Now, I could leave it in that form, but I think for this example, I'd like a simpler version of that equation. So I'm going to simplify a little bit. Z plus 1 equals, let's distribute the 1/4. I'm going to get a 1/4 x there. Let's distribute the 1, I'll get a plus y there. And then 1/4 times 4 is 1. 1 times -2 is -2. And 1 minus 2 would be -1. I could subtract the 1 from both sides, and that's going to give me z equals 1/4 x plus y minus 2. This is a slightly simpler version of that equation for that tangent plane. I kind of like having it in that form. You could also subtract the z over and add the 2 over. Sometimes we like to see our equations for planes have all 3 variables on the same side. Doesn't really matter, but this is a totally valid answer. Okay. All right, so that's an example of finding a tangent plane. But what do we use tangent planes for? Well, I talked about this a little bit at the beginning of this video. They are used for a similar purpose as tangent lines in Calculus 1, namely for the purpose of approximation. So to give you a sense of why that's the case, why we would use it for that purpose, consider this picture right here. What we have is a surface, this kind of curved surface right here. And then at a particular point on that surface, we also have a graph of the tangent plane to that point, or to that surface at that point. Okay, now what we're doing, if you notice the coordinates on the x-axis, it runs from -4 to 4. On my y, it runs from -4 to 4 here. As we go from this image to this image, you can see those intervals shrinking down. What that implies is that we're zooming in to this graph. And if we zoom in, we see that the surface that we're taking the tangent plane to is appearing flatter than it did over here. And then if we zoom in even more, it seems to flatten out even more. And the idea is that once we kind of zoom in close to the point that we computed this tangent plane to, the tangent plane and the surface look very, very similar to each other. And for that reason, the tangent plane can give us good approximations to the function f of xy that would give us this surface, as long as we're relatively close to the point that we computed that tangent plane at. Now, we do need to be careful with this because that approximation is a good approximation under certain conditions, and we're going to talk about those conditions a little bit later. But the function that gives us that tangent plane is what we call the linearization of f at ab. And we use the capital L to denote that. L of xy equals f of ab plus fx of ab, x minus a, plus fy ab, y minus b. This is just the equation of the tangent plane that I came up with down here. Instead of z, I'm writing L of xy, and then I'm using a's and b's instead of x naughts and y naughts. And again, what that means is that this, if I plug in a value, if I plug in values for x, y that are relatively close to a and to ab, then this is going to give me quantities that are very, very close to what I would have gotten from plugging x, y directly into my function f. Okay. All right. So we're going to go back to that idea of using tangent planes and linearizations for approximation in a bit, but we have something important to cover here, which is what I meant by linearizations giving good approximations under certain conditions. We need our function that we're trying to find a linearization for to be quote-unquote well-behaved. Well-behaved is a term that gets used a lot in mathematics, and it can mean different things in different contexts. But in this context, what we want is for our function to have a property called differentiability. A function being differentiable in Calculus 1 simply means that you can take its derivative. But now, in Calculus 3, where we're talking about multivariable functions, we don't just take derivatives of functions of two variables, for example. We take partial derivatives. So what does the term differentiable mean if we haven't talked about a derivative of a multivariable function, just partial derivatives? That's what we want to kind of define now. So In Calculus 3, you learn that if you have a function y equals f of x, and if it's a differentiable function, then that derivative can be defined this way. Specifically, if I want the derivative of some of that function f at a number a. F prime of a is equal to the limit as delta x goes to 0 of delta y over delta x, where delta x is what we call an increment in x, and delta y is the corresponding increment in y. We can define it more explicitly like this. Delta y is equal to f of a plus x delta x minus f of a. This is the numerator of your difference quotient when you're defining the derivative in Calculus 1. So this is just a change in y corresponding to a change in x. Now, if delta x, that change in x, is relatively close to 0, then we can ditch this limit and say that this side is approximately equal to this side. F prime of a is approximately equal to delta y over delta x, as long as delta x is pretty close to 0. Okay? Now, the approximation here means that these are not exact. But one way of changing this approximation into an equal sign is to add a very small number that represents the error. So if we're using delta y over delta x to approximate f prime of a, we might be off by a little bit, and that little bit is what we call an error. I'm going to use this little epsilon to denote that error. So that means there must be some small number, as long as delta x is close to 0, such that f prime of a is actually equal to delta y over delta x plus that little error term. Okay? Now, we know that if you let delta x go to 0, then delta y over delta x should be exactly equal to f prime of a, which means as delta x goes to 0, this error term should also go to 0. There should be no error once we take the limit, right? So this is an important part of this. Now, taking this little equation, if I solve this equation for delta y by multiplying both sides by delta x and then isolating delta y, I get this. Delta y is equal to f prime of a times delta x plus epsilon times delta x. And that epsilon is a function of delta x. It changes depending on how close delta x is to 0. So not only do we want this equation here, but we also want to restate the fact that epsilon goes to 0 as delta x goes to 0. This can actually be a way of defining differentiability for single variable functions. And in fact, your book actually does define it that way, but not initially. It uses this definition, or this characteristic of differentiable functions in chapter 3 of our book, where we talk about the chain rule specifically. I think that's like 3.5. I could be off, but where it shows up is actually at the last part, the end of that section on the chain rule, where they prove the chain rule. Calculus 1 may have been a while back for some of you. Depending on who you took that class from, it's very likely that you proved most of the differentiation techniques that you talk about. Product rule, quotient rule, stuff like that. You may remember them being somewhat cumbersome and a little messy, but most instructors, myself included, won't prove the chain rule completely. Sometimes we give a sort of hand-wavy proof. We offer a convincing argument that it's true. But the actual proof that the chain rule works in single variable calculus requires this thing. So if you're interested in that, you can go check in your book and see it. I'm not going to prove that here. But this is where we're going to get a concept of differentiability for two variable functions of the form z equals f of x, y. Okay? So to see where we're going to get that, we're going to kind of mimic this to define delta z. So delta z, the change in z as xy, as we kind of have an increment in xy at a particular point a, b, is let me back that up. If z equals f of xy, then the function f is called differentiable at the point ab if this increment in z, delta z, can be expressed in this form. Okay? Now this is fx of ab times delta x. This is mimicking this term right here, f prime of a times delta x. Okay? And skip this term for a second, plus epsilon 1 delta x. This epsilon 1 is based, you can think of this as the error term contributed by the delta x in this expression. Okay, then we also have an fy of ab times delta y, and then you have this other term over here plus epsilon 2 delta y. Think of that epsilon 2 as the error that's contributed by the change in y. So we have an error contributed by the change in x, another error contributed by the change in y, and these two terms account for those. And as was the case in this characteristic of differentiable functions up here for a single variable, we want those epsilons, epsilon 1 and epsilon 2, both to shrink to 0 as delta x and delta y also shrink to 0. So this gives us a definition of a differentiable function in two variables. And it's a weird definition. It's a hard one to use, and we're not really going to use it much at all in this section. We will refer back to this in the next section where we talk about the multivariable chain rule. But here, we just need to state it. It turns out there's an easier way to verify if a function is differentiable, and it's given by this theorem right here. So a function f of xy is differentiable at a point a, b, if the partial derivatives fx and fy exist near that point and are continuous at that point. So that gives us an easy way of verifying. All we need to do is check to see if our function has continuous derivatives with respect to x and y, partial derivatives. Okay? The point of talking about differentiability is because, like we were talking about before, if you're looking at the linearization of a two-variable function, we want the linearization to give us good approximations near the point that we computed it at. And functions that will occur for are exactly the differentiable functions. So let's do another example. In this example, I want to show that the function f of xy equals y plus sine of x over y is differentiable at the point 0, 3. And then I want to find the linearization of this function at that point. After that, we're going to use our linearization to approximate f of 0.13. I changed my mind on what point I wanted to use there. And then we're going to compare that with a true value of f of 0, 2.9. So how do we do this? Well, first of all, to verify that it's differentiable, according to that theorem we just talked about, I just need to find the partial derivatives of this with respect to x and with respect to y. So what is fx? Well, I'm differentiating with respect to x. This y is held constant, so it's going to go away. This x is the variable, and this y is held constant, so this becomes 1 over y times cosine of x over y. That would be the partial derivative with respect to x. What about fy? What is fy going to be? So I'm holding x constant now, and y, this is going to be a 1 plus, and then actually this will end up being a minus, so let me change that to a minus. Derivative here is going to look like x over y squared, negative x over y squared, cosine of x over y. Okay? So now that I have these, we need to evaluate each one of these at this point. What is fx of 0, 3? Well, that would equal 1/3 times cosine of 0 over 3, or cosine of 0, which is equal to just 1/3. Okay? I also need fy of 0, 3. What is fy of 0, 3? So that would be 1 minus, well, plugging into 0 for x here gives me 0, and the whole thing is going to go to 0, so that's just equal to 1. Okay? Finally, I also need f of 0, 3. What is f of 0, 3? Because that's going to show up in my linearization. That's the constant term. So plugging in 0, 3, that's going to be 3 plus sine of 0 thirds, or sine of 0, that's just 3. Okay? So what is the linearization then? L, x, y. So let's see, where is my return? I'm going to go back to my equation here, or my function for the linearization. This is how we find our linearization. It's f of ab, that's what we just found, f of a 0, 3, plus fx of ab times x minus a, plus fy of ab times y minus b. So putting all that together, f of ab, or f of 0, 3, that was 3, plus fx of 0, 3, which was 1/3, times x minus a. What is a here? It's 0. Okay, plus fy of 0, 3, which is 1, times y minus 3. Okay, so putting these together now, let's simplify a bit. Notice I'm going to have 3 plus 1/3 x plus y minus 3 after distributing the 1. So I have a 3 and a negative 3, which will cancel. This just becomes 1/3 x plus y. Okay, and you get this nice, simple-looking little function, which is going to approximate f of x whenever we're near the point 0, 3. And we're asked to do that. We're asked to evaluate or approximate f of 0.13 using our linearization. So let's do that. What is L of 0.13? Well, I have my function here that's 1/3 times 0.1 plus 3. And this, if you go into a calculator or something, this is approximately 3.033. Compare that to the true value, f of 0.13. That's equal to what? Here's our function f, y plus sine of x over y. So that would be 3 plus sine of 0.1 over 3. That goes into a calculator, and what you get is approximately 3.00058. My linearization gave me something that was pretty close to the true answer, and that's what we expect. One thing I didn't really draw attention to, but it was mentioned in the statement of the problem, it said that we wanted to show that this function is differentiable at this point. And how do you do that? Well, again, in light of that theorem, we took our derivatives, our partial derivatives, fx and fy. These functions are continuous everywhere that they are defined, and they are defined anywhere that y is not equal to 0. If you notice, that's the only place where the domain is going to be restricted. But if we're looking at the point 0, 3, the y coordinate's not equal to 0. So these things are defined and continuous at that point and near that point, so that's going to mean that we have differentiability for this function. That's all the time I have for this video, so I'll finish this up in the next one.